Okay, so good morning, everyone. Okay, so we are already in week 11. Okay, so there's another 3 more weeks. All right. So week 13, on the last lab session, we will have the competition run. Okay, so the details, the timing, everything, I will update you all by this week. Okay, so don't need to worry about the actual layout and so on. I will send all the details by this week once I do all the measurements and I'll prepare everything for you. Okay, but like what I showed you in the previous lectures, there will be a ramp involved. Okay, where your robot will have to go up and down a small ramp. All right, and following that, there will be some cones that you will have to sort of weave through. Okay, so that is the basic idea. But as long as you focus on fulfilling all the requirements, the checklist requirements of the mini project, then I think your robot will be ready. Okay, so the competition run is just an add-on to just gauge how well you are able to control your robot in a particular environment. Okay, so the details of the dimensions, the route, and so on, I will send you all by this week. Okay, this week I'll also place the cones and all these ramps out in the lab on Friday. Okay, so if your robot is ready, you can actually start to try it out yourself. Okay. Okay, so let's get started. So in the last lesson, we sort of jumped and went to lecture 14 first, all right? And the reason why I did that was so that we would be able to cover all the material needed to so that you have all the concepts ready to finish up your architecture for the project. Okay, so now let's go back by one topic to lecture 13. So lecture 13, we're just going to do a quick review of some of the things we have talked about and the general idea of the OS. Okay, so now that we have covered a lot of concepts of OS, and we have also sort of gotten a good idea of how OS can be used in the board that you have and in the application that you are working on. All right, we can sort of do a very good uh, comparison. Correct. So when we started off the semester, we said that we're going to learn OS and it's good, because you can multi-thread and you can share resources and things like that. Okay, but that was at a conceptual stage. All right, now we have come this far, and you have been using OS extensively, correct, in developing your project. Correct. So you now have the idea of how useful it can be, correct, if you use it correctly. All right, and now we can do a comparison back to our old approach that we used, for example, in EPP 1 and EPP 2. All right, and then we can sort of draw useful comparisons. Okay, so as we have said before, the whole idea of a RTOS, okay, is to meet harsh timing constraint that you have. Okay, so in a system where you have so many things happening, all right, you have to meet certain deadlines. And when you say these deadlines, you can still classify them, even though they are real time, you can still classify them as hard real time or soft real time. When you say hard real time means no matter what happens, you have to complete it on time. Correct? There is no excuse. All right. So in an emergency situation, like if you are driving the car and you put an emergency brake, you jam brake the car, you have to make sure the ABS kicks in. You are able to stop the car on time. Correct? You cannot say that when I jamming the car, I was busy adjusting the aircon temperature. So too bad. So it doesn't work like that, correct? So a hard real time means you have to make sure you complete it on time. A soft real time deadline or a task could be something that even if you miss a bit, it is fine, correct? It is not a very critical issue. Okay, so for example, if you turn on, press a button and the LED is supposed to light up, all right? If you light up maybe 500 millisecond later or 700 millisecond later, it may still be acceptable, correct? So even though you have a deadline, but if you miss the deadline but you still do it, then it's fine. All right, so these are the important things, correct? So the key thing when it comes to real time, when you say, is predictability and determinism. So you must be predictable. You must be able to predetermine that if I do something within a particular timing deadline, this particular event will happen. Correct. So that is the important thing. Of course, we are only looking at it from the implementation perspective. There's a lot more things in terms of proper software design which we cannot cover in this module. Okay. So one of the things, I'm not sure which particular module you will cover it, but one of the things that you should look into is called FMEA. Okay. I don't know. Does anybody know what is FMEA? Okay. So basically FMEA, okay, so it stands for failure mode effects analysis. Okay, and this is very, very important, especially when you're talking about safety critical systems. Right? That means when you design systems where safety is utmost importance, you need to do this FMEA for your software. That means you need to analyze and say, all right, if this particular component fails, correct, what are the things that I can do in my software to first detect that it has failed, correct? And if it is if I detect that there is a failure, what is the next step that I can do? Can I still carry on with this failure, or must I stop the procedure and so on? Okay, so you must do a full analysis of, if let's say something fails, what are the downstream effects, and are you able to catch this failure before it leads to something worse? Correct. Okay, so this kind of things are very important for safety critical system. Correct. So for example, in your robot car, okay, the one that you're working on, if let's say something fails, okay, so firstly, are you able to detect that maybe your motor, one of your motor has failed? So your four motors, okay, you apply PWM to them, okay, in your software or in your system, are you able to detect that something has failed? All right, if you detect that something has failed, all right, then you need to do analysis. Okay, what is the impact of this failure? Can I still carry on running with the other motors? Okay, then if I can, how long can I still carry on? If I cannot, means how do I safely shut down the system, okay, without causing any other major failure? All right, so these are things that you need to analyze, okay, that are important for safety critical systems. Okay, so again, these are some of the software design aspects that we don't have time to cover in this module, but I believe you may cover in other modules. Okay, if you do not cover it, it's good to read up on your own. All right, so that at least when you graduate, you go for some interview, and it's a company that designs safety critical software. You can just throw out these nice words, and then they'll be very impressed. Correct. Okay, so RTOS. Okay, RTOS and embedded system. Okay, so as we have seen before in EBB1, EBB2, basically what we did is we have a huge loop, right? Made a loop where we call a lot of functions, all right, to do a lot of things. Okay, so you have function 1, function 2, all right, to do a lot of different things. At the same time, you have interrupts coming in to sort of manage your encoder inputs or some data coming in and so on. All right. So of course, these kind of things are good and they do work. Okay, and they work well for many systems. Correct. And I would say again and again, do not say the RTOS is the first step in designing an embedded system. All right. If you can go ahead with designing the whole system, fulfilling all the requirements without RTOS, then go ahead and do it. All right, do not start with RTOS. You think whether you need RTOS first, is it justifiable, and then you decide to switch to RTOS. Okay, so if you do not need it, you can still go ahead with your loop and your interrupts and so on. Okay, but of course, as we have seen, all right, the main challenge with the super loop approach is, if you remember this example we went through earlier, is when you do everything in a super loop sort of format. All right, when data comes in at a time when you just finish that particular function, correct? So if just after the decode, suddenly my a new GPS data comes in, but I already finished the GPS sort of function to decode, correct? So I need to wait until I go back. All right. So of course, then you have other variations to this in terms of cutting short the function and jumping back and reassigning the sequence and so on. All right. So that adds more complexity to this whole super loop concept. Correct. So if I can move everything to task, correct. Imagine this whole system that we talk about to design or detect potholes in your environment. If I were to have put everything as a task 1, task 2, task 3, task 4, then you can visualize that everything could have been a lot more simpler. Correct. My GPS signal can be routed to an interrupt. All right. At the moment the interrupt comes in, I send a message queue. I use a message queue to wake up task 1, and then everything else will then follow through. All right. So every time GPS data comes in, I can use interrupt to start the whole process instead of going through in a sequential loop. Correct. And if let's say other loops can still carry on, I can design other loops can carry on even though I don't have GPS data. All right. I can still be updating the LCD. I can still be monitoring the switches and so on. Okay. So so if you look back to this first example, now you, with all the knowledge you've gained from your RTOS, you now see that I could have done this in a lot more elegant way. All right. And the best part is, if your system changes, correct, where you now have to maybe put in a new interface, correct? That means maybe instead of manuals, together with manual switches, maybe you have, like in our case, you have another device that can, or an app that is also going to talk to this device through some Bluetooth or Wi-Fi. All right, so I need to now get inputs from another device as well. Okay, so I can also factor that in very nicely, correct, with a RTOS framework. All right, instead of trying to see where do I insert a new function or where do I break the code and things like that. Okay, so that is the good part of switching to RTOS environment, the scalability factor. Okay, when you want to scale, like given this current project, correct, of course, after the module is over, the robot is yours, correct. So I hope I don't see it on Carousel or something. Okay, but if you still have it, all right, you can still think of enhancing it. Correct. You can still think of, okay, why don't I add a new servo motor to do some scanning, or why don't I add a LiDAR? Correct. You have used LiDAR before. Correct. You can add a LiDAR. Correct. Make it self-navigating. So you can think of enhancing it. And now with the RTOS framework already there, all right, it is now easy to sort of integrate a new hardware and put it into your whole architecture. Correct. With just the data and the interface that you need to think about. Okay, so these are the things that I would say the RTOS really helps us a lot. All right, so this is the super loop that we discussed. I will not go through again. Okay, so in RTX that we introduced you today, we have come through a lot of things. All right, I learned a lot of things. So firstly, it is a deterministic open source RTOS. Okay, another important thing, this is royalty free. Okay, so this is also an important thing that you must consider, the monetary aspect of investing in RTOS. Okay, if you want to go to the free option, okay, free option, of course, there's free RTOS. Okay, so that is an open source OS for embedded systems. They have ported it to a lot of different microcontrollers, which you can easily use. All right, but again, if it is free, means anybody can do updates to the GitHub repo, and things can just change. Right, even though you thought it was a different behavior, suddenly the expected behavior is not the same anymore. Okay, so it's a free RTOS. It does work. A few years back, we used to use free RTOS on the Arduino Uno to teach this module. All right, so it does work. Okay, and people are still using it. All right, and of course, free means your help comes from the open source community. All right, so that is the flip side to it. Okay, you don't have any dedicated support who will look into your problem to solve it if you have anything. Okay, the royalty free concept. Okay, the monetary aspect. Why is it important? Okay, so maybe before we go there, let me show you some of the other OS in the market. All right, so that you can be aware. Okay, so besides this, another popular OS that is used in embedded system is this called MicroC OS. Okay, by Macrium. Okay, so it's also a very popular operating system that is available. Okay, they do have just a few years back, they actually had a free version of this available, okay, without any restrictions. Okay, but I think they removed that already. Okay, so they still have a downloadable version where you can download and you can build your code and everything, but with a limited code size. Okay, so this is a very popular OS version. Okay, so this is a commercial grade OS. That means uh, companies who are developing and selling products are using this OS. All right. Another one that is also popular in the market is VxWorks, okay, by Wind River. So if you go down, they also have all the details here. Let me see. Do they have the OS? Okay, so here, the industry leading RTOS. Okay, so priority based, preemptive scheduling, and so on. So they do have a lot of features, all right, that is again very attractive, and it is a commercial again great RTOS. That means you pay for it, all right, and then you have the support of the company that is giving you this OS. Okay, another one that is also still very popular in the embedded world is this thing called ThreadX. Okay, ThreadX is also another commercial grade RTOS, again designed for embedded systems. Okay, and of course IoT applications. So they also have, as you can see, quite, if you see, quite a lot of them have similar sort of marketing strategy. Correct? They talk about small footprint. All right. When they say small footprint means how much memory does the OS actually occupy? All right, and fast deterministic. Okay. So again, they do have a lot of things that they talk about. All right. Whether it is applicable or it is really useful for you is something that you need to analyze, correct, based on your requirements. Okay, and the last one is one of the things that I actually talked about in the beginning, okay, of the module called Embed OS. All right, and Embed OS is uh, an, a free open source embedded operating system. Okay, sorry. So Embed OS is a free open source platform. So in fact, initially, I think I shared this before. When I wanted to switch over to ARM controllers, I was considering Embed OS as a platform to teach all. All right, because it is, again, it's free, it's open source, and you can access all these features. All right, and if you look at it in terms of board support, if you go into hardware, you look at the boards. Okay, they do have a wide range of microcontroller boards. Okay, so let's say we look for our boards. Okay, so let me see where's our board. Freedom. Okay, is it the this is the one. Okay, so our board is here. So of course this is one of the boards. So as you can see, it supports a lot of boards, okay, with a lot of different subsystems. So if you look at our board, okay, if you click on it, okay, so they explain to you the board and the sensor, the interface, everything. All right, and all the features. Okay, and this embed platform, the good part is they have a fully online software development environment, so you don't need to actually download anything. Also, you can do everything as a online environment and just download the compiled executable file. Okay, so the reason why I did not do this is because if you look at the sample code over here, okay, okay, so if you look at a sample code here, okay, you can see that they have abstracted it so much that it becomes like another Arduino. All right, and then that would have defeated the purpose of wanting to make sure you understand a lot of the sort of microcontroller concepts in a better way. Okay, so of course, now that you know all of this stuff already, you know how to control your registers, you know how to do GPIOs, your UART, PWM, everything, you can still consider going back here. All right, so now what you do is the hardware is already abstracted with all these library functions, and then you focus on the higher level objective. Okay, high level objective of what you want to achieve. Okay, so in terms of OS, embed OS, this is also a good option for you to consider, since you also have the board with you. Correct, and you have a lot of library functions, a lot of supported hardware, peripherals, and so on. Okay, so I'll not go through everything. I can leave it to you all to explore. I will send you all the links later. Okay, so let's come back to here. Yeah, so let me see. So the question is, okay, so when we say royalty free, okay, what does it mean? Royalty free means that you do not need to pay for using it, and you do not need to pay for, you don't need to pay for using it for commercial applications. All right. Okay, so in our case, uh, you need to be careful to read exactly what is the fine print. All right, so in some cases when they say it is free, royalty free means as long as you use it for academic or research, they may say it's royalty free. But if you commercialize it, they may ask you to pay. All right, that's one thing. Another thing that you need to be also careful about is individual licensing fee for product. That means you may pay a certain amount for the OS, but then you may have a clause inside that says that if you ship a product with my OS, you still need to pay per product that you ship. Okay, so you have to look at all these licensing agreements carefully when you invest in a commercial grade OS. Whether is it a one-time fee and then you can ship as many products as you want with it, or you have to pay for each product that you ship with the OS installed. Okay, so there are a lot of fine print that you need to go through to understand exactly how they are structuring this package. Okay, when you buy the OS. Okay, so these are things that, of course, if you go to a company that's already been using it, they already would have done all this work for us or for you. Okay, but if you are starting up on your own, all right, and so on, then you probably need to look at all of this. Okay, so again, these are just some of the basic things that we have already been using. Okay, in terms of the scheduling, the interrupt capability, and so on. So I'll not go through all of that again. Okay, the RTOS structure. Okay, basically we can see it from our file system itself. Okay, that means when you load the code already, we can see that it actually supports a lot of libraries. We only included some of the libraries. Okay, so when you remember when you create a new project, we selected a few options. So those are the bare minimum we need to build up a system. If you look at all the other options, there's a lot of other libraries that are already there for us. Okay, it's just that we did not include them in our applications, but you are free to explore them. All right. In terms of the kernel, okay, OS itself, it is a RTOS kernel, and it supports all the things that we talked about: the mutex, the mailbox, the timing, semaphores, everything. Okay, if you, the full source code is also there for us. All right, so it's not hidden. All right, so everything is there. So if you look into your kernel, so when you include the OS, in the most cases we include it as a library, but you have an option there to include as a source code. So if you include it as a source code, you can actually view all the sort of RTOS related files in your IDE environment itself. All right, or you can also browse through to the correct folder to look at all these files. Okay, so it is not a secret, so everything is already open and is available for us to view. Okay, so that gives you some idea on how they created all these OS related features. Okay, so task creation, deletion. Okay, I will not go through that again. Okay, so the idea of task context we have covered, where we say that when we create a task, we are creating sort of a standalone code that behaves as if it owns the CPU to itself. All right, so it has its own stack, its own copy of its registers, and so on. All right, and whenever you need to switch, okay, from one task to another task, we call it context switching. So whenever I switch over, I save my current context, restore the new task context. Okay, so I save my current context and restore the new task context, and I execute. And when I'm going to do another context switch, I will switch back. So all of these are of course happening in the background, and it's happening very fast. All right. So this helps us to achieve this sense of concurrent processing. Okay. So technically we are still running one task at a time, but because all of this context switching happens so fast in the background, it appears as if everything is happening at the same time. All right. So that is the sort of the positive effect of the OS. Okay, and prioritize scheduling, okay, which we have means that the highest priority task will be dispatched. All right, and it can always take over the CPU and run. Okay, so of course it is good because That's the whole idea of real time, correct? We want a high priority task to take over the CPU and run. But that gives us leaves us to this issue of call priority inversion, which we have seen in the tutorial before. So basically, how does it work? Okay, so for example, if I were to draw the timeline here, okay, let me do it over here. Okay, so let me draw the timeline over here so that you can see what's happening. So I have three tasks: a high priority task, a medium priority task, and a low priority task. Okay, so assuming my low priority task at t equals to 0, assuming my low priority task is running first. Okay, so of course, when we say low priority task running first, we assume that the medium and high priority were maybe blocked for some other reason. Okay, so that's why the low priority task was able to run. And at this point of time, it acquired a resource 1. Okay, and then it carries on running. Okay, carries on running. And then when it runs, okay, at this particular time over here, there is a the high priority task switches over to ready, and then it becomes run. Okay, so let's assume it switches over to run over here. So this one here is where I was running, and now the high priority task is running. All right, and at this particular instance of time, it tried to request for the same resource R1. All right, and it is unable to get it because the low priority task already has it. Okay, so when this happens, then of course it gets blocked. Okay, it gets blocked, so it goes to a block state, and then you allow the low priority task to run. Okay, so when the low priority task switches back to run, okay, and then at some point of time it releases the resource. Okay, so at some point of time it release R1. So here is where you acquire R1, and here you release R1. So when you release R1 at this time, what happens is you allow your high priority task to get unblocked, go to ready, and then go to run. So it can run. So it will now acquire R1 and then go to the run state. Okay, so basically this period here is basically what we call the period of priority inversion. Okay, why? Because a high priority task is now blocked because of a low priority task. Okay, but in this situation we call it a bounded priority inversion because you only have two tasks. Okay, so assuming that I only have two tasks, okay, then there's no problem. Okay, because that means once my low priority task reaches a point where it releases the resource, my high priority task can resume. Okay, but there's another version which is worse than this called the unbounded. Okay, unbounded priority inversion, which means I have a medium priority task. So in this situation, what happens is you assume that while I was running, okay, what will happen is at some point of time, your medium priority task transitions to the ready state. So since medium is higher, you will go over to the medium and medium will start to run. Okay, so this is a context switch. Okay, and this medium priority task will keep on running, and we do not know what it will doing, correct? So in this case, the assumption is the medium priority task is running without having anything to do with R1. All right, so it is just going to run, and at some point of time, what will happen is it will get blocked or give up the CPU or something, and then finally there will come a time where your lower priority task can run. Okay, and then it releases the R1. Okay, then only okay you are able to do a context switch back to here. So you acquire R1 and then you start to run. All right, so this is the worst or the even more worst case scenario where your entire time over here is called unbounded priority inversion. Okay, why? Because you do not know how long you take. And of course, this can get worse because there could be many tasks in between. Correct? You can have medium one, medium two, and so on. So you can have a few other tasks that come in and preempt the medium task, then another task, and so on. Okay, so you can have many other tasks that are in between M and H that can come in and still preempt and stop the lower priority task from ever getting a chance to run and release the resource. Okay, so that can be a huge issue. Correct? Can be a serious issue. All right, so that is why we in our OS we have this thing called the priority inheritance. Okay, the priority inheritance. So in priority inheritance, okay, so we covered this in the tutorial. Okay, but I'll go through this again. In priority inheritance, what happens is, okay, uh, when the higher priority task gets blocked, okay, by a resource that is shared with a lower priority task, then what will happen is the OS will do a temporary change of priority to make the lower priority task go up and match the priority of the higher priority task. Okay, so what will happen is, because the lower priority task is now raised to match the higher priority task, all these tasks that are currently in between will not get a chance to preempt this low priority task anymore. All right, so the only thing is now again between two tasks, the highest and the lowest, but only thing is now the lowest has been raised to match the highest, so now they are both at the same priority. All right, so the moment the lower priority task runs and releases the resource, immediately the higher priority task can get it and start to run. Okay, so that is basically called the priority inheritance mechanism, and this is handled by the OS itself. So you do not need to manually do anything. Okay, you don't need to manually do anything. You just need to it is handled by the OS itself. All right, so that is the good part of using RTOS system that allow this priority inheritance. Okay, so now there is two variations to this priority inheritance. Okay, there's two variations to this. One is called uh, priority inheritance protocol. The other is called priority ceiling protocol. Okay, priority inheritance and priority ceiling. Okay, the difference is, okay, in priority inheritance, what happens is you wait until the block happens. Okay, so when the block happens, then this lower priority task gets raised up. Okay, so this is called the priority inheritance protocol. In the priority ceiling protocol, it is the same idea, but you try to think one step ahead. What they say is, in priority ceiling protocol, the moment the low priority task acquires a resource that is shared by high priority task, it is automatically raised to the priority of the matching task, even though the matching task has not been blocked yet. Okay, even though it's not been blocked yet. Okay, so again, there are two variations, different schools of thought. Okay, some people say that PIP is better, some people say PCP is better. All right, so the whole idea is in PIP, if the event where there is a block happening, then you change. In PCP, you preemptively change so that you make sure that the task is able to run and release the resource, and then the high priority task, when it wants it, it can get it. Okay, so they are both systems that work. Okay, they both work, and the whole idea is you want to prevent this priority inversion from happening. Okay, so that is the idea of PIP and PCP. Okay. Okay, so that is basically these two slides here, okay, that giving you the details that I explained over there. So it's easier to explain if I draw it out. Okay, so this slide is basically giving you the explanation of the priority inversion problem. All right, and this is the priority inheritance. Okay, this is the priority ceiling that I mentioned just now. Okay, so in terms of scheduling, okay, we have the ability to assign different priorities. All right, and we know that the highest priority task will always run until it is preempted or it is blocked. Okay, then another task will run. We also have round robin scheduling built into the RTX, which will allow tasks of the same priority, all right, to run for a fixed period of time, all right, or basically what you call a time slicing. All right, so this is basically again, the idea is if everybody is the same priority, then everybody should have an equal share of the CPU. All right, so that is the whole idea. So in summary, RTX itself is known as a round robin preemptive scheduler. Okay, so again, you must be mindful of how the scheduling system works for the RTOS you're working in. All right, because uh, preemptive nature where higher priority task runs, that is by default all RTOS have that. But this round robin behavior may or may not appear in other OS. Okay, in some other OS. So for example, if you take Micro C OS, they don't have this as a default. All right, they follow strictly that whoever is highest priority will always take over the CPU. Okay, this uh, this quantum is basically a time slice. Okay, this quantum is basically the time slice that we talked about. Okay, uh, so later in the code I will show again where in case you missed it. All right, so this is basically how much time each task has before the round robin will kick in and allow another task to take over and run. Okay, so that is basically the lecture 13 to review back all these OS concepts that we have covered so far. Okay, and of course to give us a good comparison between what we have covered so far and what we are going towards, all right, in terms of OS. Okay, so that wraps up this lecture 13. Okay, so a few important things. Okay, so let me uh, share the other slide. Okay, so this is regarding the exam. Okay, so this is from the school itself. So let me share the slides. If you have somebody else already has shared it with you all, just bear with me. Okay, so the school has prepared the e-exam SOP for all students. All right, so this is the link. I will send you all another compressed document just to focus on the recording part. Okay, for the screen recording, okay, some of you all had issues in the midterm. All right, so please try to look into the issues that you are facing and try to resolve them. Okay, try to figure out what is the issue, what went wrong. Some of you all, after the test was over, said that you need a recorder for a few minutes or you ran out of memory or things like that. So you need to look through and do your own testing to verify that you are able to do a proper screen recording for the full duration of the test or exam, okay, which is about 2 hours. Okay, so you need to test your software, you need to check that you can record everything correctly, it's recording the screen, okay, and not the webcam and things like this. Okay, so do your testing and make sure that everything is ready before the exam. Okay, so again, midterm, okay, is still fine. Okay, but exam, please make sure everything is tested and you're prepared, okay, with all this necessary admin stuff, okay, before we start the exams. Okay, another thing is, again, for our module, it will be e-exam. Okay, you will be following the similar format as your midterm. That means you will still be Luminous exam with Zoom proctoring. Okay, so it's the same approach. Okay, so of course, as always, you are supposed to sit in an isolated environment that is quiet and conducive. All right. Okay, if you are unable to fulfill that, okay, then and you have very valid reasons for that, then you need to email SOC exams by 9 November to tell them what is the situation, all right, and then they will advise you what to do, all right. So most likely if you have a valid reason that you cannot take the exam at home, okay, then they may allocate you a specific place on campus to take the exam. Okay, so again, this is something that you should look into, all right, and try to preemptively uh, contact the admin office to get anything sorted out before the exam. Okay, and the last one is this getting exam results via SMS. Okay, so this is the option. Okay, so you're supposed to subscribe via the NUS EduRec system by 8 December if you want to get the exam results from through SMS. Okay, so I don't know. This seems a bit scary to me. Getting SMS result. What you're in the middle of a run or something, and suddenly you get SMS and you drop down. So I don't know. So it's up to you to decide. Okay, whether you want the SMS version or you want to do the normal version. Okay, so the next topic that we're going to be covering is on memory. All right, and this is of course a very important topic. All right, because sometimes we write code as if we have all the memory in the world. Correct, but we don't. Correct, especially for embedded systems. So we need to be very mindful of the memory that we have, and we must use it very carefully. Okay. So of course, before we go on to memory, while CG2271 is still fresh in your memory, do you want to be a TA for next semester? Okay. So I'm just preemptively trying to put out a call, even though it's still early. Okay. So for next semester, I can just say that the plan is going to be the same. We are still planning with the idea that zoning may still be in force. All right, but whatever the case, 2271 will still be at DSA lab. Okay, which means Friday mornings 8 to 10 and 10 to 12 will be the lab session. There may be an additional lab session at 2 to 4. All right, so that is for the lab. Tutorials wise, it will be online, but the schedule is not finalized yet. Okay, but if you are keen, please do drop me an email sometime after the exams or in early December, so that I will take note and I will keep you informed. Okay, in case you're not aware, the TA rate has doubled this semester onwards. Correct. So previously it was $20 per hour, now it's $40 per hour. Okay, so it's quite good money. All right, and since 2271 is still I think fresh in your mind, is something that you can consider. Okay, so do let me know, all right, sometime in December after the exams that you are keen. Okay. All right, so this is just a shout out for TAs. All right, so now let's go on to this concept of memory in embedded systems. So when we talk about a memory, okay, we are going to look at it in terms of a process. Okay, when we say process, again, we look at it in terms of a task. So when you create a task, that task or that process has a certain amount of memory, and we're going to look at how that memory is going to be organized. Okay. So these are all the things we will look at: allocation, deallocation, fragmentation, and so on. Okay, so process memory, the first thing is the code. All right, the code is basically executable code that you build. All right, basically once you write your code and you compile it, that is executable code. And this is known in advance. All right, so the OS knows your code. Okay, it is already predetermined. So the amount of space that your code occupies is already known. All right, and this is known as the text segment of the memory. Okay, in most cases, it starts at the lowest memory. That means usually 0x00000000, somewhere around there. Okay, why is because in most cases the reset vector of the controller will also point to that address. So you start off execution from the address 0. Okay, so again, I'm talking in general sense, but you will always come across controllers or processors that may have been doing things a bit differently. All right, but in generally, in most cases, your startup code or boot up code and all your text segment is starting from address 0. Okay, next comes to the data that you declare in your program. Okay, so in the way the data that you declare, there are different types. So the first thing we're going to look at is global variables and static local variables. Okay, so when you declare a global variable, that means it's available throughout the code for all the functions. When you say it's a static local variable, means it is a local variable declared within a function, but it's static. That means the contents are retained even after you exit from the function. All right, so for both of these type of variables, again, the amount of space required is already known to us, right, because you already declared them in your code. All right, so how does the when you compile the code, where do these memory elements go? So there are two segments to this. One is called the data segment. The other is called the BSS segment. The data segment is basically referring to any variables that already have been initialized. All right, so if I have this statement in my code, integer x equals 97, and this is a global variable, then you can say that this will go into the data segment of my memory. Okay, if I just declare a variable as integer y, there is no initialization, then that goes into the BSS segment. All right, and memory initialized to 0 also goes to the BSS segment. So if I put as integer z equals to 0, so that is initialized, but it's initialized to 0, so that also goes to the BSS segment. Okay, so data BSS. Then you have heap. Okay, so the heap is basically a section of memory that is allocated for dynamic memory allocation. That means while the program is running. Okay, so while the program is running, you can get some data input on how much memory you need, and then based on that particular use case, you decide to allocate a particular amount of space. All right, so you need to allocate on the go. So the OS knows nothing in advance. All right, it does not know how much space is needed and what is going to be inside that space. So you need to allow for some space to grow, and that is known as the heap. All right, and in general, we use the two functions called malloc and free to allocate and deallocate these memory segments for us. And then the next one is your stack. So stack is basically a temporary storage, all right? So it's used extensively, basically whenever you jump to a function and you have local variables within the function. Okay, and at the same time, when you pass in function parameters. Okay, so whenever you pass function parameters over, okay, so if I have a main function, okay, and I call f1 and I pass in x, y, z. All right, f1 is integer a, b, c. Okay, so how much stack space will I use? Okay, so it depends on a few things. Again, generally, okay, if you talk about normal understanding, you will say that by default, you say that everything gets pushed onto the stack. Okay, so these three variables x, y, and z will automatically get pushed onto the stack, and then when I'm in the function f1, I will retrieve this from the stack. Okay, but again, this may vary for processors. All right, for different processors may vary. For ARM, do you all know how it works? For ARM-based processors, do you all know how parameters are passed in when you call a function? Yes, no? Okay, so for ARM-based processors, okay, so this is still passing by value, okay, not by, if you pass by reference, that is still by pointers, correct? But when you pass by value or pass by reference, okay, you are passing something to a function, correct? So the question is, are you going to use the stack all the time? All right. In ARM, basically they have this rule called the ARM procedure call, all right, which basically states that for the first four parameters that are passed into a function, I will use the registers R0 to R3. Okay, so the first four parameters will pass in through registers. If I have a function that has more than four parameters, then only I use the stack. Okay, so that is how ARM works. Okay, it reserves R0 to R3 for parameter passing, and then anything beyond R3 is where it gets pushed onto the stack. So again, this is for optimization, correct? You want to save space, so you want to save time. Because pushing onto the stack and popping from the stack takes time. All right, whereas storing it into register and retrieving from register is a lot faster. Okay, so again, this is specific to ARM. Again, if you switch to Intel or Motorola or any other processor, things will change. All right. So in general, this is the memory layout. All right, how it looks like. All right, for any normal system, you have text, you have data, you have BSS, you have heap, and then you have stack. Okay. So what we will do is we'll go for a break now. All right, 10 minutes time we'll come back, and then we will look further into this memory, and then we will also explore how the memory is configured for the KL25Z board that we are using and understand how that works as well. Okay, so let's go for a 10 minutes break and I will see you all back here. Okay, now it's about 9:55, about 10:05, I'll see you back here. Okay, thank you. Okay, so welcome back. So before we carry on, there's a question here on the purpose of the other USB port on the Freedom board. Okay, so on your Freedom board, of course, there are two USB ports, right? And we have been using the one called the OpenSDA, and the other one is for what? All right, so you can always find answers relating to the board from the data sheet. Okay, so if you look in your data sheet, okay, let me share the screen. Okay, so if you look at your KL25Z data sheet, you will see that both of them, okay, the P5 SDA, P5 volt SDA, and P5 volt KL25Z both go into your regulator, which will then give me the 3 volt, 3.3 that my microcontroller needs. Okay, so if you scroll up here in terms of description, okay, so you can see that the OpenSDA, which is the one we are using, uh, basically provides us with the OpenSDA. The OpenSDA is basically the ability for us to do the debugging. Okay, once you have already downloaded the code onto the board, you can choose to just connect it to the KL25Z USB port, the other port, which will basically mean that you will just power the microcontroller, but you cannot do any form of debugging after that. Okay, so this is basically telling us that there are two possible ways to use the USB or to power the board. Okay, if you do not want to use USB to do that, okay, if you don't want to use USB to do that, you can also directly connect it to the V-in pin. Okay, so there is a V-in pin. Can't remember exactly which pin is it. Okay, but there is a V-in pin on your board. All right, so at any point of time you only connect one. Correct. So you either connect the SDA port or you connect the USB port. You do not connect both together. Okay. The other option is the P5 volt in pin. This is the one, pin 16 over here. P5 to 9 volt V in. So this is also another way of passing in a supply. All right. So this allows you to supply power to the board without using the USB cable. All right. So these are all different options that they give you, correct, to supply power to the board. All right, so you just need to use one of them. Okay, and depending on what you want to use it for. Correct. So if you want to use it for software debugging, then you have only one option, the OpenSDA USB. If you want to just power the board without any debugging, you can use the USB KL25Z or the V-in pin. All right, and important to note is both of them have a regulated output. Okay, when you say regulator means if you look at it, it passes through the regulator and then you get the output. Okay, if I choose to use direct 3 volt, either using a coin cell or a direct 3.3 volt uh, voltage in, then I need to make sure that it's very accurate. All right, because you do not want to over supply and damage the board in any way. Correct. So you want to make sure that you following this voltage range. Okay, for other cases, since it's passing through a voltage regulator, there is still some level of protection there to help prevent any over voltage from going through. All right, so that is the purpose of those two options or few options that you have. Okay, so let's come back to here. Okay, so let's look at the example here. So in this example, you have three variables declared here in main, and you are passing them into a function f. All right, and you're passing a and b into f over here. Okay, so what is going to happen? So if you look back here, so in the stack, we are creating three variables. So A, C, and B are local variables that are created within the main function. So they are stored on the stack. Okay. So when I call function f, all right, I will pass in these two variables, x and y. At the same time, I'm creating another local variable called tab. So the f occupies the three spaces here, and the main occupies the three spaces here. All right, on the stack. When my f function finishes and I return, that stack space is sort of cleared, all right, because I readjust my stack pointer. And then finally, when I exit the main function, then the stack is again cleared. All right, how the stack behaves again, I think you probably studying it or study other modules. Okay, so different processors have different ways of dealing with their stack, correct? So basically it's push and pop, correct? But whether you put the data and then you increment based on the current stack pointer, or you increment or change and then you put in the new data, it sort of varies, right? So different processors implement the stack a bit differently, but the idea is the same. You have a standard storage space and then you push and pop from it. Okay, so let's look at this example code here and try to relate whatever we have seen over to the different sections over here. Now, the first thing is the text, correct? So the code that we write is basically the text. All right, all of that goes into the text segment over here. So that is over here, the text segment. Then following that, we have two variables. One is a global variable here called string length, and another static variable here called count. All right, so both of these variables, length and count, they both will qualify into the data segment over here. The BSS segment is the global variable here, I size. All right. Okay, so let me come back here to clarify. Okay, so a static variable initialized to 0 is supposed to go into where? Supposed to go into BSS segment, correct? Supposed to go into BSS segment. Okay, so but why is it I put in the data segment here? All right, so this one is again slightly a gray area. So that's why I initially intentionally put it here. All right, so it's a gray area in a sense that when I declare a variable as 0 and it's a static or a global, should I go into data segment or should I go into BSS segment? Is actually an option. All right, so when you compile the code, correct, and the linker is invoked, it will determine where to put these variables. So under linker settings, we can actually specify for these type of conditions whether I should put in data segment or BSS segment. So saying data segment or saying BSS segment, both are valid answers. Okay, so it is a sort of configuration option that you can change in the linker. All right, so there are two options to this. Okay, so if I declare a global variable or a static variable as 0, it can be set to go in data segment or it can be set to go in the BSS segment. Both are valid. Okay, so of course, once you start to use it in the code, it doesn't switch around. Right, it is fixed. That means the compiler sort of allocates where this variable will be stored in memory and it will stay there throughout the life of the program. All right, so when you put in a different value or when I size, okay, so in this case, I size, we say go into BSS segment. Okay, when you start to use it, it still stays in the BSS segment. It's just a way of allocating data to different sections of the memory, all right, during your compile time. Okay, the next is the malloc. So over here, you see there's a malloc. Okay, so this malloc, what it will do is, it is a runtime memory allocation. So that will make use of the heap. So you do not know exactly upfront exactly how much memory you need. So during this malloc operation, then you will allocate the memory that you need. The next is your local variable. So this character pointer here, this is a local variable that is created within this function. So that will occupy the local stack. All right, so that is basically the whole idea of how, when you look at a code like this, you can analyze and say which part of the code goes into which section of the memory. Okay, of course, memory allocation and deallocation, when does it happen? Correct. So when you talk about global and static variable, okay, it is allocated during program startup. All right, so during program startup, it already knows that these variables should go into these particular segments. Local variables is basically when you call the function, correct? So when you call the function, then only those local variables are allocated memory. Dynamic memory is when you call malloc. Okay. When is memory deallocated? When the program finishes, then of course global variables and static variables are released. Okay. For local variables, the moment you return from the function, you already free up the memory. All right. And for dynamic memory is when you call the free function. Okay. So of course, all of this is there, but you can still, if you do not use some of these tools correctly, you can still sort of create issues for yourself. Okay, in the way memory is used. Okay, we'll look at that in a while. So in this example, we're trying to look at how memory can be allocated, okay, in the heap. So in this first instance, you can see that I call malloc for 3 blocks of memory. Okay, then after it allocates, there is a sort of, so the heap keep tracks of the free space that's available. All right. Of course, there are some rules to this, which you'll look at later on in the later on slides. But there are some rules that you will follow on how we allocate. Okay, so in this case, it allocated 3 blocks of units, and then it comes to this point here, and then when I allocate 1 block of memory, it allocates, and then it points to the next available space. So when I do another allocation of 4, it again points to the current space and gives me 4 blocks of memory. And then I say free P2. So when I say free P2 means whatever memory that was previously allocated to P2 has now been freed up. All right, and then I do another allocation. So again, my feed is used up, and then I do another free P3. Okay, and then I do one more malloc of 2, malloc of block 2 units of memory into P5. So of course, why did I come back here? Correct? Why did I come back here? Why didn't I carry on from here? All right, so these are the rules of how the heap will manage its memory. Okay, so we will be looking at that in a while. All right, but there are rules that you will follow to decide where should I go and look for to allocate memory. Okay, should I go back to the beginning and then look through everything, or should I start from where I left off and so on? Okay, so there are some rules that you will follow. Okay, then finally when I free up everything, then everything gets free. Okay, so let's look at some of the common mistakes that we can make, okay, when with regards to memory. Yeah, so we will be looking at defragmentation and all of that in a while. Okay, how to better manage the memory. Okay, so let's look at avoiding leaking memory. Now, if I look at this function, in this function here, I do a malloc, all right? And sorry, I do a malloc over here. Now, after I do a malloc, then what have I not done? I have not done a free. Okay, I have not done a free. So what happens? When I call the function f, I allocate some memory, I use it, correct? And if later on I call f again, what happens? I will not get back the same p, correct? Because p is a variable that is created on the stack. So the moment I exit from f, that p is lost. So I will do another malloc with another p. Okay, so what will happen is every time you allocate, but you forget to free. Okay, so this kind of issues, the challenging part is you will not see it causing a problem when you run your unit, when you run your test. Correct? But maybe if you keep running the same unit and you keep doing testing, after 1 hour, after 2 hours or so, suddenly the whole system crash. And then you cannot explain why, because it was working perfectly fine for the last 2 hours. Correct? So you cannot explain why it crashed, and then you blame everybody else. All right. So the reason is because you were allocating memory, correct, but you were not freeing it. But it never posed a problem because there was enough memory. correct? Until you reach a point where there was not enough memory. Okay, and then something went haywire when you tried to do a malloc, okay, and you did not handle any proper, or you did not do any proper error handling, okay, to check whether the malloc was successful or so on, and then you just went ahead, correct? So these are some of the things that can cause issues, which can be a big headache because it does not happen all the time. It happens after some time, correct? You leave the unit on, okay, and after 1 day or after 2 days or after some time, then the whole system crash. Okay, so it's very difficult to catch. Okay, so these are important things that we must be aware of. All right, that if you allocate, you must free. All right, and again, compilers are getting smarter. All right, but you cannot rely on them to catch all these things or give us warnings on all these things. All right, so you still have to do your own code review and code check, peer review, and all these things to catch each other's mistakes. All right, so that you improve the quality of the code. Okay. Again, another potential issue, dangling pointer, the point to data that is not there anymore. Correct. So here, for example, in your function f, you created a array, then you return p, which is basically a pointer to the start of the array. Correct. And then you try to reference that in your main function, but that is no longer valid because p was created on the stack. Okay, so the moment you exited, yes, you do have a pointer. So it does not flag off as an error because it is a valid code. You are returning a valid pointer to a memory location. But that memory location is no longer reserved for this variable anymore, correct? Somebody else can take over that memory, okay, because it's a free stack. Okay, so again, these are potential issues that may not flag off because maybe the way your code was written was after this, for a long time after I call this function, nothing else used the stack. All right, and it was working fine. Then suddenly when you added some new function, it started to occupy the stack and overrode this space, and then there's the issue. All right, so the issue was not with the new function that was added, but it was something that was already written. Correct. Again, these are things that we need to be careful about, okay, when we do our code review. Okay, so now we're going to talk about memory allocation, okay, and some of the rules involved. Okay, so in terms of memory allocation, okay, your OS itself, okay, or your system will keep track of a pointer that will keep track of the memory that is available for allocation. All right, so if I were to do a malloc of 4096 bytes of memory, so I will allocate 4096 bytes of memory, and I will uh, return the address, okay, to the variable here pointer. So pointer is now holding the starting address of this memory chunk that I have now allocated, okay, for myself. Now, of course, as we have seen earlier, it can cause fragmentation because I allocate and deallocate as and when I need. Correct. So it can cause an issue of fragmentation. So how do we deal with this fragmentation? So there's two types of fragmentation. One is called external, one is called internal. Okay, external is because I use different or variable allocation sizes. All right, and then you have a lot of space in between that you cannot use. Internal fragmentation is I use fixed allocation size where I allocate based on what I request for, but then some of it I use, some of it I do not use. All right, so let's look at this example. So in external fragmentation, if I look at this four statements here, I'm allocating 4 chunks of memory, correct? And then I do a free for the second and fourth. Okay, so the second and fourth become free, and then I try to do an allocation of 400, 200 units over here. Okay, so this 200 units, when I do an allocation, what happens? Even though I have 250 bytes of free memory, okay, there's 100 over here, there and 150 over here, 250 bytes of free memory, but I cannot do an allocation because only 150 is contiguous. All right, so this is the issue with fragmentation. Okay, what if I do internal, what is internal fragmentation? So internal fragmentation is where is caused when I do fixed allocation size. So in fixed allocation size, I pre-allocate the chunk size, right, the minimum chunk size, and then I say no matter what you request for, it will be in blocks of this chunk size. Okay, so if I assume that this chunk or this allocation unit is 100 bytes, so now every time it will be in blocks of 100 bytes. Okay, so when I request for 90, I will give you 100, but I use 90 and free 10. When I request for 120, I'll give you 200 and then 80 is free. Okay, and when I request for 10, okay, I will give you 100, but only but 10 is used, 90 is free. Okay, so you can see that. Okay, so this gives you a better way of managing it in chunks. But what happens is when you use only a small bit of it, all right, you find that you have a lot of space that is allocated but is not used, correct, because of the chunk size. Okay, so if I were to try to do an allocation here of 50, what will happen? It will fail, correct, because even though I have enough space, it has already been allocated, all right, and is unused. So it is not going to able to fulfill this request. So in terms of external fragmentation, okay, we can do compaction, okay, which we will look at in a while. So where I can sort of clear out all these holes and put all this used memory together. All right. Fixed size allocation, again, like we saw just now, it is easy to manage. All right, but only thing is you need to be careful of the fact that you may allocate a big chunk, but you may only use a small fraction of it. Okay, so let's look at this external fragmentation and how to handle it. Okay, so when I have chunks of memory allocated, like I said, internally the system must keep track of the next available hole, okay, which is the free memory, right, and the next allocated memory, which is the chunk. So I need to keep track of the hole and the chunk. Okay, so the hole is the free space, the chunk is the memory that's already been allocated. Okay, so it is basically like a double linked list, correct? One linked list pointing from hole to hole, and the other linked list pointing from chunk to chunk. Okay, so if I have a pointer pointing to this location 100, then I will be able to point to the next location, which is 400, which is the next free space or the next hole that is available in the system. Okay, similarly, 400 will point to 830. So that tells me that, okay, this is the next space where there is a hole available. This is a free memory available. Similarly, I will also keep track of the chunk. Okay, where is the uh, beginning or the next previous hole starting from. Okay, so in this case, I will also keep track of the previous pointer. Okay, so the reason why we want the next and previous pointer is we want to be able to know exactly how to go backwards and forwards from where I am. Okay, now in a free list, what we want is we probably want to have holes that are as large as possible so that I can satisfy any small request. Correct? If I have holes that are small, when I suddenly have a request that is a huge memory requirement, then I cannot fulfill it. All right. So what I want to do is I want to try to keep the holes large and then make it easy to satisfy all the small requests. Okay. How do you differentiate? So there is no particular boundary between the hole and the chunk, correct? What you need to do is you need to know how much memory has been allocated. So again, this is just giving you the pointer information only, correct? The exact amount of memory used, all right, depends on whether uh, it's sort of allocated based on the some other information that the OS will hold on to, or the system will hold on to, correct? So in this case, for example, okay, that means previously I had pointed to this location and I had allocated some memory, correct? And previously I was also pointing to this location and so on. Only thing is along the way, this in between got freed up. Okay, so basically what is happening here is you have a pointer that points to the beginning, and then you allocate a memory, correct? And then you point to the next available space, and then you again point to the next available space. Then whenever some particular chunk gets freed up, all right, then that becomes a hole. Okay, so you need to be able to keep track of these holes and chunks. So of course here in this linked list, you are only pointing to these holes, correct? So you need to keep track of all this information. The whole sort of structure of how to keep track of the information is not shown here. What I'm just showing you here is just the pointers that will point to the holes, all right, so that you know exactly where you are. All right. and where are the free spaces that are in between the allocated memory chunks. Okay, so now what we want to do is we want to look at how we can deallocate memory and then make sure that when it's freed up, we can sort of do some form of compaction to better make use of the memory space that is fully available to us. All right, so if I have two chunks of memory that is currently allocated, all right, and I free the one in the middle, all right, I can keep it as a whole, all right, because it is still two separate. So I don't need to unnecessarily move the memory around, okay, because by moving this block over, this whole space does not get any bigger, right? It's still the same space. The only thing is moved to another location, right? So I'm not fulfilling any, I'm not gaining any advantage from moving just one hole around, all right? But if I have a hole that is currently on this left side and I free up the slot in the middle, then I can do a merge. So there's an advantage of doing a merge because now I have a bigger hole that I get at the end. Okay, then similarly, if it's on the right, I can also do another merge. And if I have uh, two holes and I free up the slot in the middle, I can also have another merge. Okay, so now let's look at how we can apply this back to this example. All right, so given this example, let's assume that I do a free of this. So previously this was occupied, okay, this memory chunk was occupied, and I do a free of it. All right, so when I do a free, that means I'm telling the system that this chunk is no longer needed. All right, so I can, once I do the free, I can readjust my previous pointer and remove that particular sort of entry from the list, and also remove the next pointer and remove that from the list. All right, so now what I've done is I've practically merged both of them together and then created a single one. Okay, so again, this is uh, the policy of when to do this kind of merging, whether should I just do it for 1 byte or should I do it for this minimum 8 bytes, 16 bytes. It all depends on how the memory allocation system is working in your OS. All right, so it could be that you do it only when you have a minimum size hole that you want to merge. All right, so it is not say fixed that you want to do it every time. Okay, but you can sort of set some rules on when you want to do this. Yeah, so if your hole is only 1 byte, then yeah, you can't fit two pointers inside, so you probably need to okay, so we will look at how actually holes are created in a way that you avoid this problem. All right, you want to allocate based on some size that is manageable. Okay, so let's look at that. Okay, so the first thing we're going to look at is allocation algorithm. How will you allocate? So if I have a continuous block of memory, how do I allocate the request to get memory from the heap? Okay, so firstly is best fit. That means I will go through all the free spaces. So in this case, I have 3 free spaces. All right, and I choose the one that is the smallest that will satisfy my request. So in this case, I want 150, and I take the one that is closest to it, the smallest, and then that will give me 150. All right. Of course, this may lead to a lot of small holes. All right. So in situations like this is where you can put in rules that even after I allocate, I must have maybe minimum 2 bytes of free space just to hold a pointer. Correct. If I don't have minimum 2 bytes to hold a pointer, then I do not choose 200. I choose something bigger. All right, so these are some of the rules you can put in to make sure that after I allocate, I still have the enough additional space to put in the pointers to point to the previous or the next in the linked list. Okay, now the next is the worst fit, where I say I take the largest possible hole to satisfy the request. Okay, so again, I have to search through the entire list, okay, and I still have fragmentation. And after that, I still have fragmentation. I do not solve it. Next is first fit and next fit. Okay, so the first fit means I start from the beginning. Okay, start from the beginning, and then I go through, and the moment I get one that is able to satisfy my request, I straight away use it. I don't search anywhere else. Correct. The next one is next fit. Next fit means is the same. Only thing is if I've already started it, that means from here, let's say I already allocated 150. So my pointer is here. And my next allocation is maybe 200. Okay, then I straight away see from where I am, 200 is fine. I can take it. Okay, so that is next fit. Okay, so in next fit, you will start from exactly where you sort of left off. Okay, so in this case, for example, in this case, first fit and next fit would be the same, because if this is the start, okay, then the first fit and next fit will both come here exactly. All right, the only difference is if, let's say, I wanted to maybe get maybe 850. Okay, exactly 850. All right, of course, coming here, when I say 150 means you have to factor in the 150, I will still have some additional bytes for the pointers to be allocated. That means I may use a bit more than 150, correct? So I will not have exactly 850 left. So when I want 850, when I come here, this does not fit in. So I will go over to here and then use it. All right. So it will look at where is the best place or the next place based on the starting point. In the first fit, I will always start from the beginning. Okay, in the next fit, I start from where I left off. So if let's say the next one is 1500, okay, 1500, I will come here and I will look here, correct? So if I come in here and I allocate here, okay, so the 1500 will be allocated here. So I will automatically say this is allocated, okay, and since I already allocated this, my next available free space starts from here, correct? Okay, so if I search now for 500. If I choose first fit, okay, so let's say I take out my example. If I choose 500, if I choose first fit means I will allocate over here. If I choose next fit means I would have allocated over here. Okay, so again, I'm just assuming that I'm not considering the overheads of the pointers. I'll just looking at the actual data that I need. Okay, so the next thing is compaction to deal with internal fragmentation and external fragmentation. So we're going to focus on the external fragmentation now, how to do compaction. So the whole idea of compaction is, given this scenario where I have holes, correct? What I rightfully want is to compact this memory so the holes disappear and everything is one continuous block of memory, correct? Of course, it seems like a simple concept, right? If I look at it graphically, it's a simple concept. All right, just reassign the memory from one place to another place. All right, but of course, it is not so trivial because I need to do a lot of copying of and pasting of data, correct? And I need to change all my pointers and so on. So it does add a significant amount of overhead, correct? Because you need to move a whole lots of chunks of data from one place to another place. So conceptually, it is easy, but actually doing it is a lot of overhead for the processor. Okay, so how do we manage this? What we can do is we can keep multiple free lists of different hole sizes. All right, and then we compact based on that particular size that matches or the event that happens. All right, so for example over here, what I can do is I can create memory blocks, all right, or lists that point to different chunks of memory, and all of them sort of you can see it's all multiples of 2 or divisible by 2. And then what I do is I choose memory chunks that closely resemble the request that I have. Okay, so take for example over here, I request for 3 megabyte of memory. Okay, so if I start off with 16 megabyte, what I do is I split. All right, so I have 8 over here, 8 over here. Then again I split 4 and 4. All right, and then once I know that if I split one more, it will become too little, that I stop there and I allocate one of it. All right, and then from there, what I have is I now have a list of memory where I have split up into 8 and then 4, and the other 4 is occupied. All right, so let's look at how it works over here. So for example, now I do this. Okay, I do a malloc of so I have 1 megabyte of memory in my free list, and I want to do a malloc of 100K. So what I can do is, instead of allocating 100K to the beginning of this 1 megabyte, I split up this into a whole range of free lists. Okay, so I split up into 2, again into 2, again into 2, until I know that if I split one more time, it's not enough. Correct? So now what I can do is, I can now allocate the smallest chunk to this. All right, so the 100K is now allocated to this. All right, and this actually helps, all right, because now it becomes a bit easier for me to manage. All right, and I do not need to worry about continuously doing compaction and reassigning pointers, because I always look at how to do merging based on this particular list. All right, so the merging is basically going to follow this thing called a buddy system. All right, where the whole idea is, if two holes are buddies, then if I merge them together, I can create a new hole. The only thing is, I have to make sure that the buddies are such that they align to a proper boundary. So the boundary must be such that it aligns to the earlier memory boundary. All right, so these 2K blocks are not memories, because if I merge them, they do not align to the memory boundary at the higher level. Okay, so that allows you to create this memory hierarchy that is easier to manage. Okay, so when you are allocating memory, what you need to do is you continuously break it up into 2 by 2 by 2 until you get one that is big enough, just big enough, and you allocate. And then when you free up based on when you free, then you look at the buddy rule to decide when to merge. All right, and by merging, you are able to create a bigger hole. Okay, so let's look at this example. So in this 1 megabyte free list, I allocate 100K. So to get 100K, I need to break up first. So from so again, first I break up into 2, 512K, 512K. Then I break up one more time, 256, 256. Then I break up one more time, correct? 128, 128. And then from the 128, I can allocate 100K inside. Okay, once that is done, I ask to do another alloc of 64K. So 64K. So you have to remember that even though I allocate 100K here, this is actually considered part of the 128K block. Right? Because I split into 128K, 128K. So this 128K is already fixed for this 100K. So I will not use any more from this 100K. So this 64K, what do? I again look at the smallest size that I have and see whether I can split some more. So 128K, I can split again to 64K, 64K. So I can allocate 64K from here. All right. Similarly, if I want to do another 240K allocation, I look at the next available list, memory size in the list, and see whether there is one that fulfills this. So again, I see that the 256K fulfills this. So out of the 256K, 240K is allocated. So whatever is not allocated is considered part of the internal fragmentation. That means I will not use it. It's already allocated, but it's not used. Okay, so when I have 256K, again, I can break up the other 512K into another 2 bunch, right? 256 and 256. If I free the 240K, what happens? Okay, I free it. So when I free it, the whole 256K becomes free. But I cannot do any merge at this point. Okay, I cannot do any merge at this point. Then what happens? If I free this 256K, then what happens is I can do a merge between the 256 and 256 to create a 512K. All right, so again, it all depends on the boundary. All right, the boundary determines whether I can merge together and get a bigger memory hole. Okay, so again, so in summary, basically what we have done today is to just understand All right, the first part we did some review of the RTX, RTOS, and some of the OS. All right, and we also understood some of the concepts, okay, of why or some of the reasoning behind why you want to switch to OS. All right, and then in this lecture we looked at the memory. All right, how a code, how variables allocated to memory when we compile it, and at the same time how the process of fragmentation and memory allocation work, okay, in the system. All right, so this is quite general, all right, but it's good to have an understanding how it works, all right, so that you know that these are things that are happening in the background handled by the system for us. All right, the rules regarding how they allocate and reallocate may vary from system to system, so we need to look into that, all right, for that particular system you're working on. Okay, so that basically brings us to the end of today's lecture. Okay, next week there is I'm still trying to figure out the plan, but next week will be the last lecture. Okay, next week will be the last lecture. Exactly what we will cover next week, I will let you know by this week. All right, I'm trying to finalize it. Okay, so will you get a segmentation fault if you try to access internally fragmented part? All right, so rightfully you will not be able to access it, okay, if it is already been allocated by the heap. Okay, if it is allocated to be used by the heap means only malloc and free should be able to access that memory. All right, most mid-range and higher microcontroller units have what we call an MPU, a memory protection unit, okay, where you can specify these memory ranges to make sure that people do not try to do funny things that they're not supposed to do. Correct. So if you have already allocated this memory chunk to be used for code, then that is already fixed when you compile and download the code. So you should not be trying to override that in runtime. Correct. So you can use the memory protection unit in your microcontroller to ensure that, okay, certain parts of the memory cannot be accessed or should not have any write access during execution. Okay, so for the RTOS, it handles everything by itself. You do not need to do anything manually. Okay, so RTOS handles all our static or dynamic memory allocation that we need. So we don't need to worry about it. Okay, so the idea of understanding this is to know that this is happening in the background for us. Okay, so next week we will still have one more lecture. All right, the exact things that will be covered I will confirm and let you all know. All right, but mostly it's almost done. All right, just a few things that maybe we need to wrap up to make sure that the whole thing is complete. Okay, so continue to work on your project. All right, on Friday I will be there as well. Okay, so there are no more lab manuals. All the lab manuals have already been given. So as long as you have covered everything, all right, that we have given to you, then you are fine. For the tutorials, this week tutorial questions, if you look at it, I have given some of them as what we call exam style questions. The purpose of that is to uh, give you an idea of what type of questioning will be there in the final exam. Correct? How will the questions be phrased and what to answer and so on. Okay, project evaluation will be done in week 13 in the lab. Okay, the last Friday. Okay, so all these details I will send out by this week. Okay, so you know exactly what to do. I think for now you don't need to worry about the project competition run. You just focus on making sure all the system is fully up and all the checklist items can be fulfilled. If all of that is okay, then there is no issue in any competition run that I give. Okay, so thank you very much. I will see you all on Friday in the lab. Okay, bye.